Welcome back, my statics friends. In this video, we're going to begin with one of the most important concepts in all of statics, and that's the concept of equivalence. It allows us to take a system with many forces and moments acting on it and turn it into a single equivalent system. And there are a couple of different methods that we're going to talk about. So without further ado, let's get started. So equivalence is all about taking a very complex system with many forces acting at many points and many moments all on a system and turning it into what would be another system with a single force resultant and a single moment resultant in general, such that this object has the same behavior as the original. Now, in our methodology, and this is a little different than the one we use in our book, I'm going to call the original system as a before system, which is before I started moving everything around, and this one over here will be my after system, which is the effects of combining all of these and moving them to a new potential point. So what we have here is I have, several points A, B, and C, and let's just say at A, there's a moment at A and a force vector acting at A. Now again, these could be at any direction. They could be I, J, K's. It doesn't matter. The formulation is still exactly the same. Okay, at B, maybe I just have a force B. There's no moment value. Maybe at some other point, maybe this is D. There's a moment but no force. And then let's just say C is a point that I'm interested in, or it's a single equivalent point. We can turn this complex system into a system of forces and moments acting at the point that I want. Okay, and that's the basic methodology. Now, the idea is that if these systems are equivalent, right, then it should stand to reason that the sum of the forces or the resultant force system on this should be the same as the resultant force system on the other one. And that goes for support reactions, applied forces, everything, the net resultant, if you will. So what I can do is I can basically say that this is kind of like an equal sign, and that all my forces acting on this picture are FA plus FB. And so I would say FA plus FB, the resultant of the before, okay, is going to be equal to then FR, which is the resultant of the after. And that's kind of the basis that we're looking at. Now, what we have on this one then is, let's say that I'm after the equivalent effect at point C. Well, I could say, well, for point C, then the same should be true for the moments. And so I would take sum of moments at C for all of this. Now, we know that moment vectors are free vectors, so those just add straight in. Okay, so let's call this as my MD, that's an MD. Okay, and so MA plus MD, that's the two free moments. Okay, but then I also pick up the two forces. So about point C, FA also makes a moment vector, and we can use R cross F as our equation, and it would be the position vector R from C to A crossed into F at A. That would give me the equivalent moment at C of that force FA. And then FB, it would be R from C to B crossed into FB. Now, the first thing you see on this is that, oh my gosh, I'm getting a lot of cross products. And you do. This method is fairly long, but we'll show you some tricks as we move forward in the series, which I can kind of reduce the mathematical cumbersomeness, if you will, somewhat. But we'll kind of work on that. So that's what these pictures show, is the individual forces. And I'm just doing one force at a time. And relative to this point, here's the R cross F for A, and here's the R cross F for B. Now, these are different vectors, obviously, because A and B are different points. Okay? All right, and then the other one then is that up here, then on the other side, I would have an MR resultant vector. Now, it could be 0, it could be not 0. This is saying at point C, okay? And so that would be our effect. Now, what we will do is we will put some prescriptions on different scenarios for this guy, okay? And that's going to lead us into our discussion of the two types of equivalent system. But that's all we're doing, is we're basically just combining stuff from one picture and turning it into this after picture. All right, so the two special cases that you often see in a basic statics class. There we go. Sorry, the glare is a little horrible right there. Okay. All right, so two special cases. The first one we talk about is called the single force resultant, or the equivalent single force sometimes. And what we know on this one is that this is an object, okay, that has a known FR value And this you will always know because you can always find a resultant of forces on a before system. Okay? And at this single force resultant location, we know that the moment resultant is equal to 0. So it's a very special point. Okay? But what we don't know is we don't know the location of point C. So the vector that goes from, say, this is our origin, 0, 0, 0. The vector that goes from here to here, I don't know. But I know that this, that R from O to C would be some CX dimension times I plus some CY dimension times J plus some CZ dimension times K. Would be, that expression will always work for us here. So that would get me a vector that went from here all the way up. Okay, and with that, then I've got the point found in space. Okay, now it doesn't matter what point I choose to take the moments at, this equation will always work. So we could go all the way back to 0, as long as I do the same moment on the before picture as I do on the after picture, which is what we did up here, right? We basically chose to some moments at C. So this was my moment at C, and that was the before vector. Okay, that would be equal to the moment at C for my after vector. And that's all we're doing. Okay, and then we're just kind of playing with the pieces in the middle. Now we're not forcing equilibrium on anything. This object could be rotating, it could be spinning, it could be doing anything. Now if it happens to be equal to 0, then it's an equilibrium state, and that will be a very special case of equivalence that we'll start talking about here in the coming chapters. Okay, all right, so let's go through. So that's the first one. The second one is the equivalent force couple. Okay, and what that means is that now at my point C, I would have my FR vector, but I also have an MR vector. Okay, and in fact, the MR now is unknown. Okay, but the one piece that I do know now is that I would know the location of C. So if I say that that's R from O to C as my origin, and again, this is 0, 0, 0, then the point C location is a known location. That is R from O to C. Now, typically, if we reference this back to my coordinate system origin, just like you do in your calculus classes, I can define points as a vector. And so you would see that maybe the point C has coordinates XC, YC, ZC. All of those would be known. But it also, from calculus, we could say R from O to C is a vector of XC, YC, and ZC. So this trick of writing position vectors back to a coordinate system origin is a very common trick for turning points into vectors. Okay, and then we can do some constructions off of that we've talked about in some of our vector videos earlier on. All right, so the first one, all I want to do in today's lesson is I want to kind of take a look at just a single equivalent force resultant example. Okay, so let's take a look at an example of how we can calculate an equivalent single force resultant. What I have here is I have a beam that is cantilevered at the left end at A, and then it's 3 simple point loads. Now this is a fairly simple problem, but it should illustrate the methodology. All right, so at point B I have 100 newtons, and that is 3 meters from A. I have at point C, I have 400 newtons acting upward, which is 5 meters from A, and then I have 200 newtons acting downward, that is now 8 meters from A, and then it's another 2 meters out to the end of the beam. So what we want to find is our equivalent single force resultant. So if you remember, our equivalent single force resultant, what we said on our previous page was that there were 3 things that we knew, or 3 pieces of data about equivalence. First off, we know the resultant, and we can find that. We know that the MR value has to be 0 at that location, and that point where this is all occurring is an unknown location. All right, so what that basically means is that if I draw a before and after picture for this is what I've kind of implied. So my before picture is just the original structure. Now I go ahead and include all of the support reactions on here. This is a fixed end, so I have a moment applied. I have an AY acting up, and I have an AX acting to the right. Okay, and then I have my loads applied, and again, these all have their locations. So that's 3 meters. If I put a dotted line here, that's 2 meters. That's another 3. Obviously, this isn't to scale, but you get the sense of what it is that we're doing. Okay, the other one that we have then is the after picture, and this is the one that changes depending on whether you're doing a single force resultant or an equivalent force couple. Okay, it's we draw a similar picture. Now again, if before and after are the same, support reactions have to be the same. So I have a fixed support. Okay, so there's my MA, my AY, and my AX, And then what do we know about this? Okay, well, we've got an FR that's got to be in here. Now, I don't know the direction of this. I can find it once I do my resultant forces of all of this. And we know that this should be a vertical force because all the applied forces are vertical. But if you don't know it, draw it like this. Draw it with an angle, and this is my FR vector. And the math that we're going to do is going to prove, which directions are applicable for this. Okay, the other piece of the puzzle is that at this point we have an MR value. Okay, but what do we know about the MR? We said MR was 0 for this, so that's why it goes in. Now I've drawn it on the picture just so that I remember to draw it, but I did it kind of as a dashed arrow, and then it said that his value was 0. But I put him on there, just get in the habit. They're both there. Okay, and then the other piece is that there is a position vector that goes from some origin, and I just arbitrarily chose to set my origin at the support location. Okay, and that there is an R vector that goes from here to some point on the line of action of the force. Okay, now this one's a little bit more specific in that it has to be to the point where MR is 0. So we'll be kind of mindful of that as well. But I'm just going to write it as an R and recognize that our R vector has to be an RXI plus an RYJ plus an RZK. And that will get me the distances in the X, Y, and Z direction from my origin if I write this. Now, we don't know RX, RY, RZ, but we'll be able to find them, and I'll show you how to do that here in just a moment. All right. Okay, so let's take a look and see what we can kind of figure out. I'm going to try to slide this up here so we can keep the picture with us. So we've got that. So the first thing we have to do is we have to figure out our FR expressions. Okay, and so maybe if I pull this out just a little bit, and then we can see both. There we go. Okay, so the before picture that we're looking at, slide this up just a little bit, there we go, is we're looking at this picture here. So the first thing we're going to do is, what do we know? Well, I'm going to convert everything on the before picture to vectors. Okay, and so if we remember our basic relationship, that a vector is a magnitude dotted into something that tells me the unit vector. We've done this several times. If you need some review, go back, take a look at one of the other videos early on where we talk about this concept. This is a very important equation in vector-based statics. All right, so here's what we're going to do. So we're going to call P1, I'm going to call that as my 100 Newton force. It's acting down. That's a negative J direction. So this vector is minus 100 J newtons. Okay, P2, we said I went ahead and called that the 200 Newton force acting down. So that's a minus 200 J newtons. P3 is a 400 J Newton force, and it's positive because it's acting up. So that's this one. Our AX as a vector would be whatever this magnitude is. And again, I don't know it. So I'm just going to call it as AX multiplied by an I direction. So I'm assuming positive to the right. Okay, and that will be a Newton force. And then an AY is AYJ acting upwards. And then our moment will be the magnitude of MA dotted into a K because that's about the Z axis coming out of the paper on this one. And this is a moment. So we're going to be real careful when I do my resultants that he doesn't add in. Okay, because the first one that we do is we're going to write the resultants of the force of everything before. So we're going to go all the way down to here, but not include the moment because the moment doesn't add into this equation. Okay, all right, so when I do that, the resultant of this is going to be P1 plus P2 plus P3 plus AX plus AY. And I mean, it's a long expression, but not hard. You've done this. You've done this several times now. Okay, all right, so now let's go look at the after picture. Okay. So if I look at that, now we've got the after. So on our after picture, we have FR. This is actually what we want, for our equivalent system. So, but we're going to write it on our picture. Okay, I have an AX to the right, which is AX times I, AY times J, MA times K. These are exactly the same as what they were before. And again, kind of put kind of a separator here that you do your forces and your moments separately. Okay, and then my MR, from our definition, that was this dotted arrow that was here. Our MR is 0, so we'll leave that in there. So our equation for the after picture for the forces is R after is FR plus AX plus AY. Okay, again, the moments don't add because this is a force resultant, not a moment resultant. Okay, so when I do that, if you look at what happens on here, see if we can get both of them showing up. What do you notice? If the before and after are equivalent to each other, there should be a great big equal sign for these two equations. And what happens is if you choose your origin the same, AX and AY were the support reactions. Okay, and here are our supports. And they showed up in both equations. So it means that they don't matter. So when I do this equals this, these two will cancel those two. And so my final equation from writing before equals after, here's the whole thing, P1, P2, P3, AX, AY all added together, and FR, AX, AY all added together. Okay, well the AXs and AYs, I can cancel those. My equation is that the resultant force is P1, P2, P3. Okay, and this is the way most textbooks will write it, is they'll say that we'll find the resultant of all of the applied forces, but most of them don't do a vector-based approach, but it will work. So all I do is then I can come in and say, well, all right, I know P1, P2, and P3. We had those up here. So we can come in and we can now write our resultant equation, minus 100J, minus 200J, plus 400J, all better be equal to what? Okay, and if I do the math, minus 300 plus 400, that's a positive 100J. So my resultant force vector is a plus 100J vector. And if you go back and look at the original picture, that makes sense. All my forces are vertical. I have 300 down and 400 up. The net result, the equivalent, is 100 up. Now, what we don't know is we don't know where it is. Okay, but I now know that FR is 100J. And so we'll make use of that. Now the challenge becomes, well, how do we figure out where it occurs? And for that, we have to go look at the moment equivalence. All right, so we'll play the exact same game. All right, and we'll kind of write things down. What do we know? And if we slide this down just a little bit, we're going to go look at our before picture. Okay, so what we're going to do is we're going to find the moment of this at a point on our system, and it can be any point that we want. I chose to take it at A because I have 3 unknowns on here, and this will eliminate those guys from the unknowns, okay, especially the AX and AYs. And that's kind of a common trick on how you choose where to put your moment. Okay, and so if I take a look at it, in order to be able to do vectors, I need to know everything here is kind of an R cross an F. We're taking advantage of that relationship that we defined in the last video. Okay, so R cross F. So in order to do the R's, I'm going to do every force vector gets an R cross F on it. So I need some position vectors. So I need from A to, I'm going to choose to take my moment at A. Again, you could take anywhere that you want. It doesn't matter. But I'm going to take it from A. And so that will be a 3I, because from A to B is a vector that is going this way, right? So that's 3I meters. And then from A to C, also going that direction, is a 5I meter vector, and going from A to D is an 8I meter vector, okay? All right, so that will get us that piece. For unknowns on the after picture, we have our position vector. I know that I'm going to go some distance Rx in the I, plus Ry in the J, plus Rz in the K. Now, again, we'll just kind of, I know our position vectors here all say I, but just write all 3 of them, and then let's look at what the possibilities are when we actually start to solve this. All right, so all I'm going to do is I'm going to now write my before equation. Okay, so every force and every moment on this before picture shows up in this equation. So let's start with RAB crossed into P1, that's the 100 Newton guy, and I'm just writing the vector equation at this point. I'm not even substituting in, okay? And so RAB crossed into P1 plus RAD crossed into P2, so that's from here to here crossed into him, okay? Plus RAC from here to here crossed into P3, that's the 400, okay? But then I also get R from A to A, because I'm at this point crossed into AX, and that's where AX is acting. Okay, now we know RAA is 0, so we'll write the equation, but then we'll eliminate it. Okay, and then I've got RAA crossed into AY, so that's the point, that's this guy. Okay, and then plus the applied moment at the reaction MA is also in here. So that's, again, these are all support stuff, the last 3 terms. Okay, so that's the support that survives. All right, so that will get us that one. Now, when we do the after picture, again, we'll tuck that kind of underneath a little bit so we can still see both pictures on here. Okay, when we do our moment vectors, we have to choose the same point. So if you notice, we did it at A, and that's what I do is I write subscripts on things. So I know A is a moment vector. Okay, and we're summing moments at A and finding the net result of what's happened on before. I have to do the same point on the after. Okay, and so we're going to take A and we're going to do it again. This one's really simple. Okay, so every force is on here. Let's start with FR. So that's my R, my unknown R crossed into FR. Okay, plus R from A to A crossed into AX, plus R from A to A crossed into AY. That's these two guys at the support, plus MA, that's my MA vector, plus MR, which is on the picture, even though I know it's a zero value. And so what I've done is I've gone ahead and slashed through it and called it zero. Just write the equation, and then you can add the values, and basically the process is the same, whether it's a single force resultant or an equivalent force system. It's just whether or not you choose to slash this guy out. Okay, all right, so that's kind of what we're after. So now we're going, and then it's just a math problem. So the same game that we had before, we're going to say that these two guys are equal to each other. Okay, because equivalence says that the moment before better be equal to the moment after. Okay, so that's what we're going to do. And so if I go through and I look at what you notice. Anything with an RAA is a zero, so those terms vanish because there will be no value on those. Okay, but you also notice that these last three terms, if you choose to sum moments at the same point, which you should on the equivalence, is the last three terms show up in the after equation also. Now mine are a little bit out of order, I think. Well, no, they're the same. RAA crossed into AX plus RAA crossed into AY plus MA is in both equations. So just like before, if these are equal, then all three of those terms cancel out. And again, the support conditions don't matter. So what we get is we get an expression that looks like this. RAB crossed into P1, both of the vectors, plus RAD crossed into P2, plus RAC crossed into P3 is equal to my unknown R crossed into FR. Okay, and so that's how we can kind of start to tally this. Now it's just kind of an algebra problem. We're going to write out all the 3x3 determinants for each of these with my R's and my P's. So the first one is here, the second one is here, and the third one is here, and then the last one will be over here. Okay, and so we just basically write our equation. Now we fill in with values that we know. Okay, so the first one, I knew RAB, I knew P1, so remember IJKs go across the top. I'm doing an R on this line, I'm doing an F on this line, so R's are always on the second row, F's are always on the third. And what do we know? RAB, so this is a 3, 0, 0 vector, that's what we define. P1 is a 0, minus 100, 0. Okay, so that gets me that, and that is a solvable quantity. Okay, and then I can go write the second one. RAD, it was 5, 0, 0. Okay, and P2 is 0, positive 400, 0. Okay, so that's the second one. And then RAC has an R of 8, 0, 0. And a 0 minus 200, 0 gets me that one. So it's just, we're just filling in the blanks on this. And then the last one is the one that's kind of a little tricky because we got some unknowns in here. So IJK on the top row, an unknown RX, unknown RY, unknown RZ in the third one, and then 10, 100, or sorry, not 10, that's the 0, okay, plus 100. And again, this guy is getting the FR value that you found in the first step. So you got to find him first. And this is my unknown R on that. Okay, and so this will have some stuff that we don't know how to handle. All right, so let's evaluate this. If I do my math on my 3x3 cross product, my determinant here, this whole thing simplifies to minus 300K. Now again, I'm going a little fast through this. If you need some practice, we've got a video on vector cross products. Go back and take a look at it. But this is basically, it's K times 3 times minus 100 is the only term that appears. Okay, because of all the zeros and the way that we chose to define things. Okay, so for the second one, we end up getting a plus 2000K moment vector. And then the third one gets me a minus 1600. So this one came from here, this one came from here, that one came from here. Okay, and then we get something a little bit more complex in the last one, but it's still not hard. All right, so I get 100 times RZ times I will show up out of this one. So if I do my 2x2 on this, and that is actually should be a minus 100 Newton RZ. Okay, and then my J will be both zeros, and then my K will be 100 times RX positive will get me that. All right. Okay, all right, so that's a minus on that. So this is a minus on that. Not that it's going to matter in our end solution on this. So let's put a minus there. All right, so if I simplify all of this, if I add up all of this stuff, we end up with minus 300, minus 1600 is minus 1900, plus 2000. We're at a plus 100 Newton meter K moment for the simplification of everything on the left. Okay, and then I get minus 100 RZI plus 100 RXK. All right, now what we can do is we can now come in and I can compare terms. I can compare the I term. So although we only wrote it as K, this is actually 0I plus 0J plus 100 Newton meters K. Okay, so let's take a look at the I vector. So this says that a 0I better be equal to a minus 100 RZI. Okay, which implies then that the only way that that is ever true is if RZ is 0. Okay, so basically we're in the plane of the paper as we're looking at this. So that's one of them done. So 0 meters. Okay, the next one that we look at, let's just go ahead and skip over the K to K here. And so we've got plus 100 Newton meters K minus is going to be equal to then 100 RXK. All right, and if we look at that, that means then that in order for that expression to be true, Rx has to be equal to 1 meter. And it's actually a positive 1 meter as we start looking at that. Okay, so that gets me, so now I know where the x coordinate has to be. It's 1 meter to the right of A, because that's where I measured my r vector from. Okay, and then the last one is kind of interesting because I have a 0j here, and I have, well, there was no j term, so that's a plus a 0j there. Again, I know they're out of order, but that means that 0j is equal to 0j. What's the value of ry? And it turns out that ry can be anything. Okay, so that means that my point could be on the beam, it could be up, above, anywhere that I want, it could be anywhere. And what this is telling you, this is the proof of the statement that we made that forces are sliding vectors. Okay, that basically I can take a force and it has the same moment effect if I slide it anywhere I want along its line of action. Okay, and so that's kind of a cool point that comes out of writing it this way that you'll know. And so I know then that my answer for what this equivalent single force resultant system looks like is that there's an FR of 100 newtons acting upward in the J direction. So again, we've set up our sign convention, Y positive up, X positive to the right, and Z positive is out of the page. Okay, and so this 100 Newton force is acting at 0, 1, and anything. Okay, so it could be anywhere. And that's the picture that you get for the single force resultant equivalent of the system that I just showed you. Okay, so it's pretty cool. And so with that, I think that we'll go ahead and stop the video here. In our next video, we'll show you some force couple resultants, but this one's getting kind of long. But that's the process. It's the same equations up here no matter what you do, that we want to write those and make sure that we're following the same logic. This part never changes. The only thing that's going to change on this has to do with basically the pictures that we illustrated. Are you in a single force resultant case, or are you in an equivalent force couple case for those? Okay, and so usually in a problem on a quiz or a test in my class, or even in a textbook problem, it will say find the equivalent force couple. You will see these words, and so you'll know exactly which one you're looking at. And when you see those words, that's your clue to what are the unknowns, the assumptions about it. So we showed you the first one, which was that FR is known, MR is 0, point C is unknown. In the next video, we'll show you how to handle this case. Okay, again, FR is done exactly the same way, but now we have an unknown moment value, okay, but the load will be an unknown. So that R vector that we had, where we said before, remember we wrote the statement that was here, CXI, or sorry, wrong one, down here, that the R vector was RXI plus RYJ plus RZK, that vector will now have known values of Rx, Ry, and Rz. Okay, and so you'll know where the point is in relation to your origin. You'll be able to write that directly, and that makes your math a whole lot easier as well. So, all right, well, I hope that's made sense to you. As always, if you've got any questions, leave them down in the comments down below, and I'll be happy to respond to it. Otherwise, if you found the video useful, please toss us a like or a subscribe, and we will see you all next time. Happy engineering.